like root x minus 1 over root x plus 1, you think, let's just make the whole root u, right? What's the problem there? Then you have to solve for x in terms of u. So if u is this root business, that will tell you that x is something like u squared minus 1 over u squared plus 1, and that's no help. Then you have to differentiate this or something. But if you multiply and divide by root x minus 1, so if we go root x minus 1 root x plus 1 times root x minus 1 root x minus 1, meaning just multiply and divide by the same thing, and the thing we choose it so that it cancels the square root on top, right? Then what do you get? Then the square and the root cancel, and here we have a root x squared minus 1. And that's a secant fraction. So it becomes root. I mean, the first part of it with the x is just a u substitution. Then the one with the 1 is a secant. So that brings us to our lesson today, actually, in a nice way. Because, I mean, I didn't have to look for a segment. The lesson is 7.5, right, which is strategies for integration. And the answer, like, how do you integrate something, is you have to be clever. With some integrals, you have to know which substitution to use, and you have to know what not to do, right? So, you should remember, there is only two techniques. There is u sub and integration by parts. That's all. That's all we use in everything. There is a substitution, or you do it by parts. In other words, there is the chain rule and the product rule. That's all. So, those are the ones you have to use. Now, which one do you know when to use? That's a matter of practice. That's a matter of experience. So you just have to develop this experience, intuition a little bit to see what to use when. Okay. So the book, so this section 7.5, in the beginning there is the table, and you guys have the book, right? So there is the table in the beginning of section 7.5, which is the table of integrals you should know. So I don't know how you want to do this, stick it to your fridge or something, but you have to know this, right? What am I talking about? Yes, at least one person is listening. There is a table of integrals in the beginning of section 7.5 that you have to know. Yes, Rashid? You just have to know it. No, those are the basic, it's a basic table of integrals that you have to know. Cosine, but it has other things, like it has, like one of the integrals in there, in this table is this, like integral of dx over root of x squared plus minus a squared, and this is log of x plus root of x squared plus minus a squared plus a constant. And another one in there is just the, I mean, you could do these during the exam. It would just take you a long time, and you can just use this. You can just say this is in the table of integrals and just write that down. So that's okay. But yeah, integrals generally are hard. It's not like differentiation, where you just differentiate, and it'll always end. That's not the case here. You could try using a chain rule. The integral could become more complicated. You could try using an integration by parts. Again, it could become more complicated. So it's a process that may never end. Whereas differentiation, you differentiate, it simplifies until it ends, for sure. So that's why here, for one thing, some integrals is impossible to do. And some, you have to be really clever. Some people get their PhD thesis just solving one integral that nobody has been able to solve, or solve one differently. At least like 60 years ago, people used to get PhDs like that. Solve one integral, and that's it. So what is the strategy for integration? So basically this section, the book gives you some tips on how to go about integrating, right? Let me just write those tips down and go from there, right? So the first is simplify. The second is try use of. The third, so try use of because that's the easiest one, right? That's the one you want to do. This is not really like a surefire way, like I'm saying, right? So classify them. In other words, in terms of, are they trig integrals? Are they rational functions? Are they, can they be done by integration by parts? So does it look like islate? Or are they radicals? Basically radicals with quadratics. Or so square root of something quadratic, or the nth root of something linear. So this is the basic strategy the book gives, right? So first of all, we should try to just simplify the situation and see what happens, right? So for example, you have some integral like x minus 1 root x minus cube root x over x. Like something like this, you should just first simplify it, right? So everyone here knows how to do this thing I wrote. Does it look doable? No? Yes? Just say so if you can. If it doesn't look doable. Yeah? Sorry? So the different, so it's like trig integrals, entirely trig integrals, sine, cosine, sine, tan, secant, tan, all that. This is when you have a sine and an e to the x, or an x and a sine. So if you have multiple types of functions in the same thing, then you choose isolate, then you try to do integration by parts. Right? So this is something that might look like x squared plus 1 and then a sine x, and then a dx. So you have something algebraic and something trig in the same integral. That's what I mean by it doesn't look like isolate. Is there some sort of integration by parts that you think? So do you know how to do this? Please tell me you know how to do this. This is like the first formula, you know. All you need is x to the n is x to the n plus 1 over n plus 1. That's all you need for the first one, I think. Yeah, that's all you need. So, can you do it? How does one do it? Expand. Just expand. So multiply the x by this, x by that, 1 by this and 1 by that, and it becomes a polynomial. And none of the powers are -1, so you don't even have a log, you just have. So do you need me to do this, or are people comfortable with this? Okay, I'm going to assume your silence means yes. Okay, so trig is, let's try this a little bit. What kind of u sub? Sometimes there is an obvious u sub. For example, if you get an integral that looks like something like sine of e to the x, cosine of e to the x, e to the x dx, right? Something like this, or something like maybe it's sine of log x, cosine of log x over x dx, or maybe this one, the e to the x is in the denominator as a e to the minus x. So these types of problems, they're sort of not so subtly hinting at a u substitution. Because an exponential inside a sign, or a log inside a sign, that would be unthinkable to integrate. So we can barely integrate products of logs and sines. Now put a log as the angle in a sine, that's too much. So there must be a trick. Understand? So you see, what is the trick here? Or what is the trick here? It's like an obvious u sub. Right. So take u as the log x or the e to the x. Because what happens? So first of all, if it is in the denominator like this, first thing you should do is move it to the numerator. Because e to the minus x in the denominator means e to the plus x in the numerator, right? So move it to the numerator. And now this is exactly the derivative of e to the x. So you should let u be e to the x, so that du is e to the x dx. So this just becomes sine u cosine u du, and then you go from there as a trig integral. Right? Now it becomes a trig integral u. Same thing here. Here you should make u log x, because its derivative is exactly 1 over x dx, which is already in the integral. So the 1 over x dx part, that is taken care of by the du. Log x's all become u. So this integral just becomes, again, sine u cos u d. Right? And this kind of thing happens all the time. So for example, like I could give you something like x square root of 1 minus log x squared. Something like this. Right? Where if there is a 1 over x and you see a log x somewhere in your integral, turn the log x into u, because 1 over x is its derivative. And this is just not only true for log x, it's for any function. Any function whose derivative you see in the integral, you can substitute it away. Any function whose derivative you see in the numerator of your integral, you can substitute it out. So for example here, I can make the substitution log. Why? Because its derivative, yeah? Because its derivative is there, right? So you make the substitution log so that its derivative 1 over x dx is there. And then this becomes what? The dx over x part again is the du, and we're left with the 1 minus u squared, which is arc sine u. sine inverse u. And then of course you have to remember to go back to x, which the problem was in terms of, right? So what is that? Will be arc sine of log x. Yeah.
Second one, can't we take all of high limit as u?
This one?
Yeah.
Take sine log x as u. Does it work? Okay. Oh, okay, good. Yeah. Or sine is the x as u, yes. It's true. Thanks. I thought it wouldn't work. But this is a sure way of doing it. Okay, so the book has lots of examples of this. By the way, let's finish this one. How does one do sine u, cosine u? Integrate sine 2x. So if you know, but also you could make this something so that this is its derivative, no? So there's two methods here. Again, so it's kind of like the same two methods you were saying. You could make, so we could make, I don't know, t be sine u, so that dt is exactly cosine u du, so that the integral becomes integral of t dt, which is t squared over 2 plus a constant, which would be sine squared u over 2 plus a constant, which would then be sine squared of log x over 2, right? Or the other thing we could do is multiply and divide by 2, and then use the fact that 2 sine u cosine u is sine of double the angle. So no integral yet, so it's just what's inside is sine of 2u. And then because it's sine of 2u, you can integrate it. It becomes what? Minus cosine 2u over another 2. So those 2's make 4. And now you go back. So this is minus a quarter cosine of 2 log x. And apparently that's the same as this. Right? So what double and half angle formulas do you need to absolutely know? Sine squared and cosine squared. This 2 sine cos. Sine. I guess you know it, so it's okay. Yeah. So you need to know the sine square is 1 minus cosine 2 theta over 2, and the cosine square is the one with the plus. The 2 sine cosine is the one that gives you sine of the double angle. You of course need to know that, you know, sine square plus cosine square is 1, that secant square is 1 plus tan square, and that cosecant squared is 1 plus cotan squared. Yep. Yes, and what else? Am I missing something? Right, so you have to know, obviously, that tan is sine over cosine. What else? Am I missing like an important formula you need to know? So often when we are doing this, like even powers of sine and cosine, we have to use these. And then when you do integrate it, to go back to your original form, you have to turn sine 2 theta maybe back into that one often. These are the Pythagorean ones. You should know those. What else? I think those are the really important ones that you should know. So are there any questions about like U sub sort of deals? Do you have any questions related to that? Okay. So U sub is basically what? Look for something whose derivative. Look for something in the integral, right? Not look for something generally. Look for something in the integral whose derivative is in the integral. In the numerator, basically, of the integral. So that's the general strategy of U sub. You want to look for a function whose derivative you already see. Then there's the strict function integrals. You know, the sine n, cosine m, or the tans and the secants, or the cotans and the cosecants. And here, if either n or m is odd, they're good. Whichever one is odd, take it out and turn the rest of that function, which is now an even power, into the other one. And here, the good situation is when either tan is odd, is an odd power, or secant has an even power. So if this is even, or this is odd, this is an odd, then you are great. Then you're done. It's a polynomial, you can integrate. But if this is even and that one is odd, then you're in trouble, and then it's a case-by-case situation. Okay, and what do rational functions look like, and what do you do to them? You think of roots? No, that's not rational. Function is what? What is a rational function? We just did this last class. What is a rational function? That's a rational number, yes. Yeah. So nobody knows what a rational function is? I explained this last class, like literally 2 days ago. You guys really have no idea? So what is the numerator and the denominator? Okay. So you're describing proper rational functions, yeah. Rational is just polynomial over polynomial. Rational is some polynomial divided by some polynomial. So no sine, cosine, root, anything like that in there. Just some polynomial over polynomial. So this is something that looks like, right, so this is something that looks like integral of, I don't know, ax cubed plus bx squared plus something over some other powers. Maybe 7x squared plus 3x plus 2 complicate. Something like a polynomial divided by a polynomial, where there's no roots, no signs, no exponentials, no logs, no inverse functions, none of the crazy functions, just the x squared, x cubed, x 4, all of those in the numerator, in the denominator, like we did last time. And how do you do these integrals? Right, you do long division, and then what do you do with the rest? Partial fractions. This is the one you do with partial fractions. You were here on Tuesday, right? You weren't. Okay, no. If it is bigger, you divide first. You long divide, long division. It doesn't. Rational is just polynomial over polynomial. A proper fraction is when the numerator has lesser degree than the denominator, and something like this will be improper. And something like this is like a 13 over 5, which you can write as a 10 over 5 and a 3 over 5. You take the quotient and the remainder, right? And then you get something that's not a rational number. I mean, that's not a fraction. Something that's an integer plus a fraction of part. That's what you do here. You split it. You take the part that's a polynomial with no denominator, and then you get a remainder over the same denominator, and then you do the method of partial fraction. Okay, so trig integrals, we sort of have an idea. Rational ones, you have to do partial fractions. That's a pain, but that's the way to do it. Right? Partial fractions are long and complicated. You have to find constants A, B, C, D, E, F, G, whatever. It can be complicated, but it's a way to do it. You can get an answer, right? Then there's integration by parts, right? So you remember the trick for this? Integration by parts? If you have a mixture of functions in there, like an inverse function and an algebraic function, like an exponential and a sine, something like that, a logarithmic and an inverse, then you know I have to, go by this rule. If it's an inverse, you choose it as u, and the other one is dv. If there is a log but no inverse, then choose the log as u, and the other as dv. Then you differentiate the u, integrate the dv, and integral of u dv turns into uv minus the integral of v du. So you flip their roles and hopefully get an integral that you can integrate. It doesn't answer the problem, it just turns it into a different integral. Right? I had some complicated examples of this prepared. I don't see them, so maybe let's just. Oh, I almost forgot. I have a attendance sheet. Oh, that's what this is. So this is the long class, right? So in today's date, sign your name. In your name, please. Yes. Yeah. Later. So what time is it now? And we go until when? 9:15, right? So maybe like 5-7 more minutes. Then we start. Because it's the first quiz, I made it especially easy. But seeing as nobody listens to anything I'm saying, I'm not really sure anymore. And I think I chose problems very, very similar to the ones I gave you in the sheet. There were 9 problems you had to know how to do. This is from those problems. As we go on in subsequent quizzes, I'm going to up the difficulty a little bit. I was looking at the past midterm. This is baby stuff. What I'm giving you is baby stuff. So I don't want some of you complaining later, like the quizzes were easy, but the midterms are hard. The midterms are hard. So I thought, okay, this is the first quiz, let me just give you the problems that, this course, the midterms, you will feel the difference from calculus 1. It's not like baby questions. Here's a graph, but is the limit 1 here or 2? No. It's going to be not like that. Right? I don't mean to scare you. It's very doable. But you have to do it. So are we passing around the time? Yeah. So like integration by parts, if you have something like, so if I have something like, we have integration by part on the quiz today, right? Yeah, good, okay. So that's, so I guess we are doing that. And then radicals, I want to talk about something. So if you have roots of quadratics, right? Or some nth root of just a linear thing in your integral, then it's always possible to just switch it, make the whole thing u. Okay? Because then what do you get? Then you get u to the n is a linear thing, so you just get a dx is n u to the n minus 1 du. So dx can be immediately replaced without introducing any roots or any complicated business in the denominator, and the integral just becomes easier to do, right? So, and what about quadratics? What happens with roots of quadratics? Can someone tell me? Yeah, something like that. The quadratic is like, this is altering substitution, yes. And how do you do it? What type of quadratic gets what? So, inside a square root, I can have a something plus x squared plus some number, right? I could have minus x squared plus a number, or minus a number x squared plus a number. Or I could have plus x squared minus a number, but I can't have minus x squared minus a number because it's inside a square root, and there should be something positive there. If it's a minus x squared minus a number, that's obviously not going to apply. So these kinds of things, what do you do? So generally you write this as x squared plus whatever number this is, write it as a square. Yeah. This one, x becomes a tan. This one is the sine, and this one is the secant. Yeah. That's still a number, right? So, say you have square root of x squared plus, you don't mean a squared plus bx. It's another that's the whole thing is a constant, right? Okay, it doesn't matter. These are numbers, right? So this is a number. So it's the square of a number. If it's a positive number, right? It's the square of a number. So that number squared. So this would be x would become something like root of a squared plus b tan theta. You should just think of this as whatever number is there, you think of it as a square. Where's the sheet? Is it going around? Okay.